Zoom, I think we can start the webinar today. So good morning, good afternoon, good evening, everyone. I think that we have audience from everywhere, from over the world. And today that we have the RAS webinar, and we're honored to invite David Hunt that to join our RAS webinar. David is serving as a 2025 president of Informs. He's also currently a vice president in Oliver Wyman's transportation practice, focusing on the national and regional policy issues, transportation operations and strategic planning, network modeling, and operation research. David has also worked with clients on the six continents and across different modes of the transportation, with a particular focus on the railway. And in 2017, David has received the Informs President Award for the work on the pro bono analytics and the Informs ethical guidelines. So we're happy to have David that to give us a presentation. And the webinar today will be the topic on the quantum technology and operational research with application to the railway industry. It is a very interesting and also trending topic and emerging technologies in the railway industry, and I'm looking forward. So I need to hand over to David.
Okay, let me share my screen. Hopefully this.
Lily, I just want to add, Dave is also the Railway Application Session Chair in 2022 and 2003, and he was also the founding member in 1995. So I want to just mention he's one of our long-time contributor. Thank you.
Thank you, Professor Zhou.
Thanks, Yai. I was actually the first editor of the newsletter back in '95, so I've been hanging around with this group for a long time. All right. So let me get going here. Hopefully you can see this fine. So this was a difficult audience to prepare for because you have different backgrounds, and I had to assume something. So what I've assumed is that this audience knows optimization, that you know computer programming, but you're new to quantum computing. So again, feel free to ask questions if something isn't clear. And I'm also going to warn you that some of the slides are very dense. It's almost written more like a report than a presentation in places. So I've sent the slides through, and I'm happy to make them available afterwards, or they can be posted on the RAS website, if anyone wants the details. So don't feel like you need to read everything on every slide. So I've broken it into four sections, a very brief introduction, and then I'll give a little background on quantum mechanics and how that relates to quantum computers. I'll describe how quantum computers work, and how the applications that people are looking at. And then this is a railway section, so I will talk about railroads toward the end. So the reason I got interested in quantum computing, last year when I was president-elect of Informs, it was brought to my attention that the United Nations had declared 2025 as the International Year of Quantum Science and Technology. And so there is a community within Informs doing work in quantum computing, quantum algorithms, and we decided that it would be good to leverage the UN proclamation and showcase the work that our members are doing. So I put together an ad hoc committee, and they've been looking at webinars. We had a book club to kick off the year. We had several presentations in Indianapolis at the Analytics Plus meeting. We had a couple of vendors there. D-Wave and Quantum Computing Inc. had booths in the exhibition hall if you were in Indianapolis. The Computing Society at their meeting in Toronto had sessions. We're planning some in Singapore in a couple of weeks, and then there will be several sessions in Atlanta in October at the annual meeting. There was a special issue on the Informs Journal on Computing that obviously started well before we created the ad hoc and started this, but that issue is now out. If you have an interest, it's volume 37, issue 1 is on quantum computing and operations research. And then we're also getting into some of the advocacy efforts, educating members of Congress on quantum computing and the role of the operations research community in that, and connecting our experts with policymakers and news outlets so that the voices of our members can be heard in this discussion, because there is a lot of interest in this topic now. Overall, we're looking, like we did with artificial intelligence, at how we can, at Informs, create, sustain and organize our efforts in quantum computing this year and beyond this year, continuing it forward. The other bit of introduction I want to do is quantum technology is a broad term, and it includes things such as quantum sensing, which are sensors that are orders of magnitude more sensitive than classical sensors. I mean, they're detecting things like temperature, gravity, measuring time, electromagnetic fields. Then there's quantum computing, which will really be the focus of what I'm talking about today. There's also quantum communication. So you'll hear about breaking, hacking into, breaking the RSA code, breaking cryptography with quantum computers, and creating more secure communications with quantum computers. So, and then there's new emerging things like quantum storage I've been reading about. So there's a lot of quantum technology, but the focus is on computing today. All right, let's dig into a little bit of the physics of this. So the first thing I want to talk about is superposition. So a lot of people are maybe familiar with Schrodinger's cat. So Aaron Schrodinger, a physicist, developed this famous thought experiment where you put a cat in an opaque box and you also put in a vial of poison. Now, at some unknown time, a mallet might break the vial, releasing the poison, which uh, unfortunately would kill the cat. No cats were harmed in the making of this thought experiment, don't worry. Um, but without looking in the box, the cat can be thought of as existing in two states. It can be thought of as being both alive and being dead. And this is really superposition. In quantum mechanics, it refers to the ability of a particle to exist in multiple states, just like Schrodinger's cat. Now, we're all familiar with bits in classical computing. Classical computers have billions of transistors that can be on or off. And these binary digits or bits are one or zero, and they're the basis of all the calculations that we do. They're controlled through logic gates. Boolean operators such as and, or not are applied to these billions of bits to create software applications. I mean, we're not typically dealing with it at this level. The issue is that classical computers are approaching a physical limit. So transistors are currently about 20 atoms apart. At 5 atoms, they're going to start interfering with each other. So we're going to reach a physical limit there. I mean, when's the last time your laptop really was much, much faster than your previous laptop? The solutions are either we can try to write more efficient code, or we can look at alternatives to classical computing. And one of those is quantum computers, where the basis is not a bit, but it's a qubit, a quantum bit. So quantum bits are based on the spin of electrons or the polarization of photons or other methods. And qubits, just like Schrodinger's cat, can exist in multiple states. It's neither a 0 or a 1, but a possibility of both due to superposition. And quantum computers use gates, but they're not the same gates as the logic gates in classical computers. Some of them are, but you have new things such as Pauli X, Y, and Z gates that rotate a qubit around the X, Y, and Z axis, or a Hadamard gate that creates a superposition of states. So to try to make this a little clearer, on the left-hand side here, our classical bit, and a single bit is either a 0 or 1, very simple. It's either on or off. But with a qubit, it can be represented in this Dirac notation using two basis states. So if you can see my cursor, this line with a 0 and a bracket, this is a ket in Dirac notation, and it represents a column vector of 1, 0, which represents the 0 state. And then the second one here, with the 1, is a column vector of 0, 1 and represents the 1 state. So when we're talking about a qubit, all we're really saying is that it's the linear combination of these two basis states. So the psi here is the state of the qubit, and the alpha and the beta are the amplitudes. Now, the amplitudes, if you square them, represent the probability of that qubit being either a 0 or a 1. And this is based on Max Born's rule, where the amplitude square equal 1. Probabilities, of course, have to sum to 1. Now, a common way to think about this is with something called a Bloch sphere. So if we have our 0 basis state at the top and our 1 basis state at the bottom, instead of a bit where it's either a 1 or a 0, a qubit can be anywhere along this sphere. It can be any point on the sphere. Now, you can take the Dirac notation and you can convert it into something using these angles, theta and phi, and you can represent the state of the qubit on this sphere. Now, when you measure the qubit, it collapses randomly to a 0 or 1 according to the probabilities based on the square of the amplitudes. So this is how a qubit can represent a lot of different states other than just 1 or 0, the way a classical computer does. Another thing that we have to look at with classical computers is something called entanglement. And that's a phenomenon where electrons or photons become interconnected so that the state of one directly impacts the state of another one. So it's called teleportation. It refers to the transfer of an unknown quantum state from one location to another, although it isn't really a physical transfer. If it was a physical transfer, it would be traveling faster than the speed of light, which isn't possible. So it's not physically transporting anything, but changing one particle changes the state of the other one. So in this science article, it talks about Chinese researchers who entangled a pair of photons 1,200 kilometers apart using a satellite 500 kilometers above Earth. Albert Einstein called entanglement spooky action at a distance, which is maybe the best definition I can give it. Another way that you can think about entanglement in a more intuitive way is if you have two coins, and if you were able to entangle coins, if Alice flips a fair coin in New York and it comes up heads, and Bob flips an entangled coin in Jacksonville, it also has to come up heads. If Alice's comes up tails, Bob's will come up tails. The two are entangled and they will do the same thing. So in classical computing, what entanglement does is it allows quantum parallelism. So in classical computing, parallelism refers to being able to execute multiple tasks at the same time. And in quantum computing, this definition changes because entangled qubits aren't working on different tasks. They can actually work on the same task in parallel. So the state space can grow exponentially with the number of qubits you have. So if I have 10 qubits, I can consider 2 to the nth or 1,024 cases simultaneously. In classical computing, it would require 1,024 processors, each updating one value in parallel. So you can see where this can be very helpful in terms of combinatorial optimization problems. Now, of course, the traveling salesman solution space still grows more rapidly. It's 2 to the n-1 factorial, where n is the number of nodes. But with enough entangled qubits, there are some problems with massive search spaces that could have all the possible solutions found at the same time. And an intuitive example of this is with a maze. So if I'm on a classical computer and I'm trying to solve a maze, I mean, there's probably more clever ways to do it, but basically you're searching one path at a time to find the right way through the maze. In a quantum computer with these entangled qubits, I can search all the solution spaces at once to identify the correct solution in the maze. The last bit of physics I want to talk about is tunneling, and this gets into quantum annealing. So tunneling refers to a state where rather than having to go around a barrier like you do in Newtonian physics, you can actually tunnel through something, through an energy barrier. And so an intuitive way, again, to think about this is a ball rolling over a hill. So in classic Newtonian physics, the ball requires a sufficient energy to be imparted on it to get it up to the top of the hill so it can roll down the other side. But in quantum mechanics, the ball can tunnel through the hill. So tunneling can be leveraged to solve some types of optimization problems. So many of you are familiar with simulated annealing, where we search along the curves, trying to find the global minimum of something and avoid the local minimums. In quantum annealing, you can use tunneling to find the global minimum by tunneling through the energy barrier to find the minimum point in a search space. So I want to talk a little bit about what that really means and then kind of tying this together. If we take something, an NP hard problem, like traveling salesman problem, where we're starting at one point, visiting all the locations, ending at the same point and trying to minimize the distance, the way that you do that with quantum computing is that you first would convert it to something called a quadratic unconstrained binary optimization, or a QUBO. Now, a QUBO, you take a constrained optimization and you move the constraints into the objective function. And there are a lot of papers out there with different types of optimization problems that have been converted into QUBOs. So you can find those out there. I've listed one reference here that has several examples, including a traveling salesman example. Now, once I have this QUBO, so I have everything in my objective function, it turns out that that's mathematically related to something called a Hamiltonian. Now, a Hamiltonian in physics is just the total energy of a system. It's the kinetic plus the potential energy. So from the QUBO, I can actually go then to the Hamiltonian, specifically an Ising Hamiltonian, which is a very simple form that uses binary variables in the Hamiltonian. And I can create two Hamiltonians. One is a Cost Hamiltonian that represents the objective function, and the other is a mixer Hamiltonian that explores the solution space. So then this can go to a quantum computer, and there are algorithms such as the quantum approximate optimization algorithm that finds the minimum energy of this quantum system. So I take this Hamiltonian and I find the minimum energy of it using the quantum properties of the computer. So it's using the entangled qubits and tunneling to efficiently search the solution space. And when it comes out with the minimum Hamiltonian, the minimum ground state energy of this system, that in turn is really the solution to the QUBO, which in turn is the solution to our traveling salesman problem. So that very simplistically is how this works. Now, I want to be clear that quantum computers are not, a golden ticket solving NP hard problems all of a sudden, that this is a probabilistic solution. So it is giving an approximate solution to it. But the expectation is that quantum computers are going to solve much larger NP hard problems more accurately than classical computers can. So you might say, how much faster are these things going to be? And that's a great question. There's a term, quantum supremacy, which refers to a point at which quantum computers can do tasks faster than classical computers. So the Chinese Academy of Sciences claimed in 2020 that its quantum computer was 100 trillion times faster than a classical supercomputer. Google reported that they had a 70 qubit system that solved a problem in seconds that would take 47 years on a supercomputer at Oak Ridge Labs. And just last month, Google claimed their Willow chip could perform a standard benchmark in under 5 minutes that would require 10 septillion years on the fastest supercomputers today. Now, when you look at the details of these, often you'll find they're research papers, and these are theoretical results, not actual results they've achieved in a lab. And also, I would encourage you, don't count on your PowerPoints being 10 septillion times faster with a quantum computer. For some applications, the overhead of a quantum computer actually makes them slower. But eventually, quantum computers will be much faster at selected problems. And the main areas people are looking at are simulations, where you're able to simulate at a quantum level the interaction. So for example, if you're developing new drugs, you can start simulating how those drugs at an atomic level will actually interact in the body. improving crop production, climate change strategies, improving battery life, testing different chemical reactions in batteries, new material science. So this is one of the huge areas that they see for quantum computers. The other is optimization. So, we've talked about the traveling salesman. So it's applications like that. I mean, it's huge in finance, looking at portfolio optimization and risk management, and of course, railroad dispatching. And then cryptography is another big one, and people are very concerned about that in terms of people being able to hack in. There's something going on now, harvest now, decrypt later, where people are grabbing as much information, bad actors are grabbing as much data as they can now in hopes that they'll be able to crack it with quantum computers fairly soon. If you talk to Amazon Web Services or others, they claim that they're already post-quantum secure, so you don't have to worry about it if you have things stored on their cloud. But it is a concern in terms of cryptography. So are these things real, and is anyone using them? Before I go there, I need to talk about something called coherence and decoherence. So for quantum computers to work, the particles have to be arranged precisely, and they have to vibrate in unison, and this is called coherence. But if any of these particles are very sensitive to outside disturbances, cosmetic rays, electromagnetic interference, I've read if someone sneezes next to one of them, you can throw them out, and it leads to decoherence. So a method being used to try to maintain coherence is to cool them near absolute zero, which is approximately minus 460 degrees Fahrenheit. But even with the cooling, they're still prone to disruptions. So the thing with decoherence is that you need to dedicate a large portion of qubits to error correction routines that keep the computations running. And a key metric that's used for that is something known as fidelity, which is just 1 minus the error rate. So where we are with that, company Quantinuum announced they have surpassed what they call 3 nines, 99.914 fidelity using a 2-qubit system. The commercial viability will likely require 6 nines before it's something that can be used reliably.
So David, when will it become available? Do you know that when it will become available, quantum?
I have a slide on that. I will answer that shortly. Good question.
Thank you.
So we're currently in an era known as noisy intermediate scale quantum, indicating that they're really unreliable at this point due to the large number of error correcting qubits required. Oops. I will get to your question, Jonas, shortly, but I need to talk about two different types of computers, though, two different types of quantum computers. One is quantum annealing, and the other is a gate-based or a universal system. So quantum annealing is what I was talking about, and it's a very specialized quantum computer just for optimization systems. So it's using quantum tunneling, and it's focused on just solving these combinatorial optimization problems. A gate-based system is a more universal system like the computers we have today. So it's based on these Pauli gates and Hadamard gates I talked about a little bit before. And in a gate-based system, you can program it and do the simulations and a lot of different things. You can do things like Shor's algorithm, which maybe you've heard about for breaking RSA encryptions, or Grover's algorithm, where you can find a character in a large string of characters very efficiently. These algorithms were actually written in the 1990s before the quantum computer hardware was available to even test them. But in both types of these, the quantum annealing and the gate-based systems, it ends up being a combination of classical and quantum computers, where the classical is doing pre and post processing and ensuring feasibility of solutions, and the quantum computers are doing these short-lived high computation calculations. So a leading company doing the quantum annealing computers is D-Wave. They were founded in 1999. They sell quantum computers. They also offer cloud access. In May of this year, they released a 4400 qubit Advantage 2, which they claim is orders of magnitude better than their Advantage 1 computer. you can actually get time on these, and you can create applications using their Ocean Developer Toolkit. And they have several customers for their systems: Volkswagen, Toyota, Los Alamos Labs, Lockheed Martin. On the gate-based systems, one of the leaders is IBM, and they sell their computers as well or provide access on the cloud. In May 24 last year, they claimed to have over 600,000 registered users for their Qiskit development, software development toolkit, people testing out their algorithms on their systems. Their plan is by 2029 to deliver a large-scale fault-tolerant quantum computer with the ability to run 100 million quantum gates on 200 logical qubits. And by 2033 plus, note the plus on that, they're claiming that they'll have a fully functioning billion gates, 20,000 logical qubits. Now, I need to say, when these quantum annealing systems with 4,400 qubits and IBM saying they'll have 2,000 qubits in 2033, there's a difference in the qubits when you're talking about these systems. On the annealing systems, you don't need the same level of precision that you need for gate-based systems. So you can have more qubits with more errors in them, which is why you're going to see higher qubits on the annealing computers. And then there's a whole host of companies developing this. I mean, through May of this year, there's been 2.65 billion in venture capital funding already. And this is just a small sampling of some of the computers. I mean, you see Microsoft, Amazon, Google, companies you would expect, and then a lot of other companies, Quantum Computing Inc., PsiQuantum, Alice and Bob, Quantum Circuits, that are exploring this space as well. And the thing is, there isn't just one way of building a quantum computer. There's a lot of things being tested. So there's one thing known as superconducting, where you take two superconductors separated by a thin insulator in what's called a Josephson junction, and you're sending a microwave pulse between them, which creates these qubits that are in superposition, entangled qubits. There are others, such as photons, which are using photons of light. You have trapped ions, where you're taking positively charged ions. It's just an atom with some electrons removed. And they're trapping in the trapped ions, you're trapping these in electric and magnetic fields. So you're trying to get them to vibrate as coherent qubits. There's neutral atoms. So instead of a positively charged ion, you have an atom that has a neutral charge. Then there's quantum dots in silicon, where you're taking these electrons confined in a 3D space, and you're fabricating them within silicon, because we have a lot of experience in building silicon-based chips. Now, each of these has advantages and disadvantages, and you can see at the bottom, I've just put a sampling of companies that are exploring each one of these. But even within these, like superconducting, for example, there's a lot of different types of superconducting. So it isn't clear which one of these is actually going to come out on top, whether there will be one clear winner. I know some people who feel there will be one clear winner out of all this, or there may be multiple solutions, or it may be a case where one is a winner this year and then it gets leapfrogged in a few years. Microsoft, I mean, this isn't complete either. Microsoft is doing something called topological qubits. Yeah, Jonas.
How trustworthy are the claims about the future, do you think? Do you think it's likely to become the truth, or likely become a reality, or is that just, yeah?
Here's your slide. So I think it is likely to become the truth. The question is really, when will quantum computers have their chat GPT moment, right? So back in 2020, we were talking about artificial intelligence, but nobody was really paying attention to it, or at least not in the commercial side. And then all of a sudden, chat GPT hit. So will it have a chat GPT moment where all of a sudden everyone is interested in it, or will it grow more slowly? So I think we're going to start seeing it grow more slowly, where we're going to start getting solutions, particularly on the quantum annealing side. So IBM, we've talked about. Google claims that by 2029, they're going to have an error-corrected quantum computer. PsiQuantum is claiming by the end of 2027, they will have a commercially viable quantum computer. I know a venture capitalist who has put his money behind this bet. D-Wave, their CEO, now D-Wave, remember, is doing the quantum annealing, not the gate-based systems. But D-Wave CEO in January said they're delivering value today and they predict growth in their commercial applications with this new Advantage 2 computer that they've just released. Alice and Bob is a company based in France. They say they'll have useful quantum computing by 2030. IonQ, quantum computing not only feasible, but will be commercially ready by 2028. So with all these companies and all this money going into it, I think that we will see them in the next few years. And it's not just these big companies or small companies that are working on these, countries are investing in it too. So China has invested over 15 billion in quantum computing, and other governments, France, Germany, India, Japan, UK, South Korea, and the US are investing billions in this technology. So hopefully that answered your question, Jonas.
Yeah, you did. What about the errors? What about the errors?
The error rates?
Yeah.
Yeah. So I mean, they're creating these. They're working on getting that down. As I said, they're at 3 nines. They think they need to be at 6 nines in terms of precision. They're creating these logical qubits now, where they're putting groups of qubits together, where some are handling the errors, and then you have the qubit doing the computation. Uh, that is the challenge, is to get the error rate down, but they seem to think that they're on a path to do that.
Thanks.
In terms of applications, I mean, there are a lot of applications. This is an IBM quantum computer installed at the Cleveland Clinic in Cleveland, Ohio. I've read that this was in their research lab, and then I was talking to someone who had knowledge of it, and they said, no, it's in their main lobby so everyone can see it. But Cleveland Clinic is partnered with IBM, and they're using quantum computers, testing it, researching it to screen and optimize drugs. The BMW is looking at creating better car batteries, modeling the chemical reactions in the batteries to come out with longer lifespans for the batteries. They're looking at optimizing charger station locations, aerodynamic performance. As I mentioned, there's a lot of government interest in quantum computing. The Department of Energy, for example, energy modeling such as fusion research. Airbus is looking at sustainable aircraft, a zero-emission aircraft by modeling hydrogen fuel cells, modeling the quantum, at an atomic level, what's going on with hydrogen fuel cells and how to make those into sustainable airplane engines. Volkswagen has been looking at real-time route optimization with quantum computers. This slide, I'm not going to spend much time on it, but really it's the financial industry that's been leading the way on quantum computers so far. I mean, the larger people, JP Morgan Chase, there's actually someone on my ad hoc committee who works at JP Morgan Chase, Goldman Sachs. I mean, these companies have quantum computer teams on board looking at portfolio optimization, fraud detection, risk management, option pricing, and a lot of different things. And of course, the transportation logistics companies are looking at this. So there's a paper out there on vehicle routing problem, solving a vehicle routing problem. One of the authors works at JB Hunt. We see Deutsche Bahn looking at algorithms to optimize train schedules, and FedEx looking at a variety of things from route optimization to package tracking, demand forecasting, and overall supply chain optimization. Now, you might be asking, what about artificial intelligence in quantum computers? Is there an opportunity there? And there absolutely is. So we think that the two of those are really going to enhance each other. They're going to elevate the other one. So on the artificial intelligence, what impacts will that have on quantum computers? Well, AI can help with some of the hardware design by searching through and helping to identify and design these computers. It also can really help with the speed up of the quantum algorithm development, including code writing, in Ocean or Qiskit or any of the other development toolkits that are out there. And it can help identify use cases that can best leverage the power of quantum computers. Now, quantum computers, the impact on AI, it can increase the computational power to help train larger, more powerful AI models. Also, indications are that quantum computers are going to have a huge energy consumption advantage over classical computers. So, I mean, there's a lot of concern about the amount of energy these data centers and training these AI models has. Quantum computers will operate at a lower energy level. And leveraging superposition entanglement allows AI models to be trained with fewer parameters and less data on a quantum computer. There are some papers and claims out there on this topic. All right, I did promise railroads, so let's move on to railroads now. So how can quantum computers benefit the railroad industry? So these are some of the things I've seen and thought of. I mean, certainly more efficient routes and schedules. So quantum computers, improve route planning and scheduling by solving larger, more complex models. Improve traffic management, looking at real-time data to better predict traffic patterns and optimize flows. Maybe you can get into dynamic blocking, things like that. Greater sustainability. I mean, the railroad industry doesn't even really need to lead the way on this, with companies looking at battery technology, hydrogen fuel cells. We just need to think about how that would work within locomotives. But we can get better sustainability, advanced material design, aid in the development of new materials, creating lighter and stronger components that are less susceptible to failure. Increased safety through quantum sensors. As I said, they're orders of magnitude more sensitive than existing sensors, so they'll better detect and predict mechanical failures. And upgraded cybersecurity with communication and protecting against cyber threats. Now, I know that US DOT has a lot of interest in quantum computing, and last year they had a webinar and also a day workshop in DC where they were digging into quantum technology and the benefits it would have on transportation. One of the focuses, they had several professors there from MIT that were experts in quantum sensors. So they're very interested in how these sensors might be able to better monitor infrastructure such as bridges to predict failures before they occur. And I think this research would directly benefit the railroad industry, and something that certainly the rail industry should be paying attention to. So the work I've seen on railroads, it's been pretty limited and mostly coming out of Europe so far. I mentioned already the Deutsche Bahn work. I mean, they teamed with Cambridge Quantum, looking at how to re-optimize train timetables after delays occur. And on their webpage, they claim that they're looking at other areas in quantum algorithms and how it can improve their systems. There also was a paper. A lot of the research is this Professor Domino, and I know we have someone on the call here who has co-authored a paper with him recently, but out of Poland. I mean, there's a paper I found on the Baltimore Light Rail Link, and they were looking at how to manage train traffic under random disturbances. This was actually funded through the National Science Center and the Minister of Education and Science in Poland, doing this work on the Baltimore Light Rail Link. So the way that these work, if you'll allow me one more kind of talking through an algorithm a little bit, and I'm explaining someone else's work here, so please forgive me if I make a mistake. But this railroad dispatching and conflict management, the problem statement is really that a disturbance affects traffic in a portion of a railway, and the trains are not able to meet their original timetable. So they've assumed that it's a single track, it has sidings, so you can do meets and passes, and the track is divided into blocks where you can only have one train occupying a block at a time, and all trains run according to a timetable, which initially is conflict-free. Now, their objective function was to minimize the weighted sum of the secondary delays. So when an event occurs, you have the primary delays But then after the event is cleared up, you have secondary delays as you're trying to get back to schedule. And so it's these secondary delays they're trying to minimize. And the constraints are the typical constraints you might expect, minimize passing time, you have single block occupancy, you want to avoid deadlocks, rolling stock circulation, just, a train has to arrive before it can depart. You have capacity constraints that you have to worry about. They tested this on two lines on a Polish railway. Line 216 had 3 trains in each direction, and then you have line 191 that has 9 trains in each direction. And the authors, they say that they're aware that these are really trivial from the point of view of a professional dispatcher, but they were testing the algorithm to see how it would work. So they converted the problem into a cubo, as we've discussed, and then an Ising-Hamiltonian, and you can see the math in their paper. They solved it with a quantum annealer. They also solved this using a classical computer, using a job shop formulation. So what this really did was it allowed them to benchmark the solution quality, the solution speed, and the ability of the quantum computer to solve these problems. Now, I'd like to report that the results were a great success, but they were mixed. They ran this thing on a D-wave quantum annealer. It was a 2000 Q. It had 2000 qubits on it. The paper said that toward the end of their research, the Advantage 1 was released, and they did some testing on that. Now that remember I said the Advantage 2 was just released, and D-Wave claims it's orders of magnitude more powerful than the Advantage 1. So it'd be interesting to repeat this with the Advantage 2 to see how it does. But as I said, the results were mixed. So for the smaller one, the one that had 3 trains in each direction, they were able to solve the problem. The one that had 9 trains in each direction, they could not get a feasible solution. They were able to solve both of the problems using Cplex. But the authors said that their intention, was really a proof of concept demonstration of the applicability of quantum annealing in this field, and the goal has been achieved. And I would agree with them. They achieved their goal. They solved it with the smaller problem and showed that it was feasible. And now that the computers are getting faster and faster, it'd be interesting, to see, just how much of a larger problem can be solved. The authors were also very encouraged that just this small size problem, and this was back in 2021, could actually be solved and was, within reach of these quantum annealers. So my last slide, other than some references, is a challenge to the RAS community. So should RAS play a role in advancing quantum computing at railroads? So I've laid out a possible roadmap here if RAS is interested. So I think we first need to, find all the research that's been directed at rail in terms of quantum computing to understand what work's been done in North America and around the world regarding the use of QCs, quantum computers at railroads. We need to find out what research outside of rail, such as batteries and hydrogen fuel cells, would be relevant to the rail industry. We need to identify the types of problems at the railroads where we think quantum computers could provide a significant boost in terms of operations and productivity. And then we need to start benchmarking these, roll up our sleeves and start coding and benchmarking these against existing classical computers, just the way that the researchers did on the lines in Poland. And finally, we'll be in a position, when these hit, whether it's 2027, 2028, 2029, once they hit, we'll be in a better position to have rail as a leader in this new technology. So that's my presentation. I have some selected references here, a few names such as this one that you might know. I would also encourage you this ORMS Today article, the second reference. This was written by my ad hoc committee at Informs. It's a really good article talking about optimization and simulation and a little more technical than what I've been talking about here, but I would encourage you to read that. But all of these are pretty good references. So with that's my presentation. Thank you very much for your time.
Thank you, Dave, for the informative presentation. And there are also a lot of new information, at least to me, about the emerging trend of the quantum computing, as well as what is the current stage, that including the limitations of it. And we also received a couple of questions that in the Q&A. So I think I'm going to go through for it, and then we will open for the Q&A that for the audience. I guess there are a lot of interesting questions here as well. So we have, I think there's more of an information. I think Don Grist was sharing information that there will be a National Quantum Consortium hosting a quantum technology showcase in July 17. I think that's also an interesting opportunity for audience that who would like to learn more. And our RAS chair has also indicated that the ASU team, Arizona State University team, has also collected some online sample codes for the quantum computing simulators. I do see that there is one question that mentioning that in some of the recent Groovy webinar, the researcher at Close stated that I think more of that limitations that 5,000 of qubit quantum annually computing can handle at most 160 binary qubit variables, like kind of small optimization problem. I think that's kind of coincidence with David, one of the cases that you mentioned. There is a research that has also mixture of the result, where that for some of the large optimizations that will. So maybe I'll hand it over to you to give more of the feedbacks on this one.
I'm sorry, you were breaking up a bit, and I didn't quite get all of the question.
Oh yeah, sorry. Yeah. So.
Is this Eric?
I want to ask.
Yes. So we are.
I'm not sure whether you're there.
Yeah, we were in the question that from.
Is it me that's breaking up, or?
Yeah, my question was whether there are also issues with the errors, because what we've seen in management recently is that there's not a lot of oversight. So basically, when people just cheat, nothing happens. And I wrote a paper about it, Science wrote it, where I talked a bit about it. That's basically when you have issues in papers, that nothing happens, and actually as a whistleblower just got like backlash. And so my question was a bit, with all these claims about the future, do you think that there's a lot of errors in the current quantum literature already?
So, but you're not talking about errors in the qubits themselves, the qubits spelling. You're talking about false claims in terms of.
Yeah, more about the literature. That people just claim things that are not true.
Well, I think that there is certainly a bit of hype going on in terms of it. I mean, I would think that some of the academic papers out there, I mean, they are peer-reviewed. I mean, things that come through the Informs journals are peer-reviewed, and I would hope that would get caught if people are making false claims there. Now, what you see in the press, I mean, the press will sensationalize things. I mean, if you read the New York Times article a couple of months ago, the headline was something like Microsoft invents a new state of matter for their quantum computers. So, it's not a solid, a gas, a liquid. They've created this new state, but when you actually dig into the details of it, Microsoft is investigating these topological qubits. And so they've written a paper, and in theory, there is this state of matter. They haven't actually created it. So a lot of stuff, when they claim, it's a trillion times faster, 100 trillion times faster, it's a theoretical result that they haven't actually achieved, but the press will pick that up and make claims that that it's real, that it's happening, because if the press says in research they found this, nobody's going to read their article. So.
Yeah, but the problem is also with Informs journals, when there's an error in a journal or when there's research misconduct, you cannot actually publish about it. So I tried this with Lamar Peers and Organization Science, and he does not even look at the evidence at all. So he just claims, yeah, we do not do that. So the literature cannot never be corrected. So that's why I'm asking, because the literature is just not correcting itself anymore. So that's why it's always important to ask the expert what's actually true.
Yeah. No, well, I mean, we certainly do what we can to try to catch those. So I see, Nicola, you have your hand raised. You have your hand raised. Would you like
Nicola?
to say? There we go.
Just too many buttons. Yeah, exactly. So, as maybe one of the authors of a recent paper, so we do our best to do things as open as possible. But after doing so, we have more questions after publishing the paper than before we started. And would give you just an example from our work is basically we looked at hybrid algorithms, and we talk about D-Wave in particular, which kind of combines conventional and hybrid algorithms. And we were able to run and get better results in some instances. But the question is how much is thanks to quantum, and what is actually solved on quantum. So what we are doing now is taking a step back. We have here Alexander Schiller with me. So we actually want to see what we can solve actually with pure quantum algorithms. So without the whole beautiful black boxes of D-Wave or anyone else, but to go gradually. And once we mature that, then we want to take onto development of hybrid models ourselves.
So I see
and your noise also comes into play. I'm sorry, because we have the
very interesting, Nicola. So, but you cannot publish that in literature, so it's not in literature, these issues.
So we are working on it now. So it's okay. we shall talk about it in a couple of months.
Okay. I see some of the questions here. I'd like to try to get a few of them here in the chat. So I see Eric Wickham's question, or more of a statement. He said that in a Groby webinar, it was stated that a 5,000 qubit quantum annealing computer can handle at most 160 binary variables. So that's a pretty small problem. I mean, I can't dispute that. I mean, I know the claims from D-Wave that they are actually solving problems with their Advantage 2 with 4,400 qubits. But I mean, there's going to be a lot of claims out there. We'll have to see exactly what can be solved, which is why I think we need to test things and see where we are with stuff. The question about the cost of quantum computing. I mean, a D-Wave quantum computer will cost you about 15 million. You can access it though on the cloud. IBM, I know, will give you 10 free minutes a month on their system to run algorithms. And then it's like $1.60 a second beyond that. The cost is only going to come down. There is a company that was at Informs Quantum Computing Inc. that has a different type of quantum annealer than D-Waves. It doesn't have to be cooled to minus 460 degrees, and it costs 300,000. So it'd be interesting. I would love to test it and see exactly what we could do with that system. The cost also, I will say, with some of these other systems like D-Waves is a huge maintenance cost in keeping them cooled. Success in combining deep reinforcement learning and quantum computing. Yeah, that's an area, a lot of interest in that. There was an article that I saw where they were training a AI algorithm on reading stop signs using a quantum computer, and they were able to do it with a significant reduction in the number of features needed to train the model and in the time to train the model. So there's a lot of interest, a lot of research in that, how quantum computers can advance AI. Quantum annealing focuses on the ground state of a quantum system. Yeah, I don't know the answer to that one, whether that's probably a bit more physics than I really know. I do know that with these ground state systems, they don't necessarily return a feasible solution. And so that is an issue. And that's why you're using classical computers to try to keep it realistic. I know the same thing's going on with AI. I saw some research out of Georgia Tech on that, where they're using AI to solve optimization problems, but it's not returning a feasible solution. So you're using more classical algorithms to keep it feasible, but leveraging AI, or in this case, quantum computers, to um, to return something that is a feasible solution. So Clark heads up quantum computing based optimization of railway networks. Oh, great. That's terrific, Clark. Glad to hear that. I hope I have time to go to that one. Um, okay. I think we are at the top of the hour. If
Yeah,
hopefully I answered everyone's question as best I could.
yeah, we will also have the recording that be uploaded in the RAS YouTube and shared with everyone. That Dave has also shared with the presentation. So I think like more of the questions or any other thing that feel free to reach out to me or reach out to our RAS sections. And we are again that we're very honored to have Dave that you join us to give us very interesting and emerging topics in the quantum technology in the railway. Thank you, Dave.
Oh, you're welcome, and hopefully I sparked some curiosity in some of you in the topic.
Thank you.
Thank
You're
you.
welcome. It's
Goodbye, everyone.